Solving Algebra 1 problems. Topic: sets of real numbers. In these questions we are to name the set or sets to which each number belongs. So before that, just a word about the most common sets of numbers that you ought to know about. First, the natural numbers. The natural numbers are 1, 2, 3, 4, 5, and so on, and we write ... These are the numbers that would have been discovered by humanity anyway. They seem to sort of be built into nature, as it were, and we use them for counting things. So prehistoric humans would have used them for keeping track of how many sheep there are, for example. And how can we symbolize this set? Well, we use the capital letter N, often written like this. Next comes the integers. So the integers include all the natural numbers and 0 and their negatives. And the best way to write it, in my opinion, is as follows: -3, -2, -1, then 0, then 1, 2, 3, and then ... And putting these ... on both sides, because someone can just mentally fill in the blank. The symbol for this is a capital Z, which I believe stands for Zahlen in German, which means number, something like that. These are called the integers. Some books and some people consider 0 to be so special that what they do is they create a sort of set in between these sets called the whole numbers. So that would be 0, 1, 2, 3, 4, 5, ... And what symbol do they use? Well, they use a W. W for whole. The very phrase whole number is very ambiguous in maths. Some people believe that it includes 0. Some people don't. And some people even believe that it includes the negative numbers. I strongly advise against using this term for that reason, because we don't want ambiguity in mathematics. So please don't use this term, but just be aware that it exists. Next comes the rational numbers. Examples of rational numbers include, let's use blue, 1/2, 6/8, 17/11, -23/46. Okay, so what am I trying to say? A rational number is an integer over another integer, but the integer on the bottom must not be 0. Now, I can't write down the rational numbers in this way and then do a ... That would be very sloppy indeed, because how can anybody possibly guess at the pattern here? And someone might think, you know what, I'm just going to write down a half, a third, a quarter, a fifth, like that. Very systematic. But if I do it that way, how am I ever going to reach 2/3? I never will, because this will go on forever and ever. So the best way to specify and pin down the rational numbers is to use a template. Just like this. Write down P on top and Q on the bottom, then do a little colon, and then say what P and Q are. Say that P and Q are integers, and very importantly, say that Q is non-zero. And then put it in a pair of braces like that to indicate that it's a set. Now, what is the symbol for this set? The set of all natural numbers. The symbol is Q. Doesn't make much sense. I believe it stands for quotient, which is what P over Q actually is. It's called a quotient. Okay? And is there a set which goes even beyond the rational numbers? They would seem to be perfectly adequate, right? As you can always find a rational number in between any pair of rational numbers. Just add them together and divide the answer by 2. So they would seem to fill up the whole of the number line, right? Well, beyond these are the real numbers, which includes all of the rational numbers, and then also, crucially, the irrational numbers. The most famous irrational numbers being the square root of 2 and pi. These are just 2 examples. There's infinitely many irrational numbers. And what that means is you can never, ever, no matter how hard you look, find a rational number, a pair of integers, one divided by the other, which is exactly equal to the square root of 2. That's what that means. But hold on a minute. Where are the decimal numbers, I hear you ask? Well, just before I say a word about those, I should probably tell you that the symbol for the real numbers is R, which really does make sense. And let's talk about the decimal numbers then. Okay, so let's consider 1.43. I claim that this is just a rational number in disguise. This is just 143 divided by 100. Okay, what about 0.5678 repeated over and over and over again? 0.5678, 5678, 5678, which we write like this. How would you handle that? Well, that's 5,678 divided by 9,999. And if you don't believe me, look on your calculator. So, decimal numbers which halt, or the official word is terminate, a terminating decimal, or repeat themselves, the official word is recurring. These types of decimal numbers are actually rational numbers in disguise. It's troublemakers like the square root of 2 that cause us to think about what are called irrational numbers. As the square root of 2, when you observe its decimal form, goes on forever and ever and never repeats itself. It never gets stuck in a loop or a cycle. Okay? So, to recap, natural numbers, that's 1, 2, 3, 4, 5, and so on. Integers, that's all the natural numbers, and 0, and their negatives. Rational numbers, that's one integer divided by another non-zero integer. One integer divided by another non-zero integer. N, Z, Q. Natural numbers, integers, rational numbers. And then the real numbers, whose symbol is R, include every single number on the number line, including irrational numbers like the square root of 2 and pi. And now we're going to solve these problems. Okay. Negative 15. What set does that belong to? Well, negative 15 is an integer. Negative 15 is an integer. So we could write z like that. And because it's an integer, that means that it's also a rational number, because we can always write this as negative 15 over 1. And because it's a rational number, that also means that it's a real number, because it's on the number line. So you can write z just by itself, but if you want to have a complete answer, just write z, q, and r. 11 is a natural number. It's in the sequence 1, 2, 3, 4, 5, ... And of course here I could write nzqr, but to save time I'm not going to. What about the square root of 30? Well, the square root of 30, if you type it in on your calculator, you'll observe that it's one of these messy decimals. So it's certainly not a natural number or an integer. But is it a rational number? The answer is no. Any square root of any whole number that is not a perfect square number, which, just to remind you, is 1, 4, 9, 16, 25, and so on. The square root of any whole number which is not a perfect square number will be irrational. It will be irrational. Okay? So, how are we going to say what set this belongs to then? Well, we could just say the real numbers, right? Just be aware, though, that in some books they will use this fancy I symbol sometimes to stand for irrational numbers. I don't know why they do that, but sometimes they do. Another way of doing it is like this. They say it belongs to the real numbers, but definitely not the rational numbers, and they do it like that. So that's another way that you can do it. Now 17 over 3, well, that would be 5 remainder 2, or 5.6 recurring. And that is a rational number. That's a rational number, of course. 6 is a natural number. 0, is it a natural number? Well, you may object and you may say, but I've read in my book that 0 is actually included in the natural numbers. It's very unfortunate, but this is a point of dispute or a point of convention differences. You have to know what conventions, what traditional way of doing things there are in the place that you're working at. I would say that 0 is an integer. Nobody would dispute that. But some people might say, it actually belongs to the natural numbers. But if you really want to be unambiguous, you can write natural numbers like that and write down greater than or equal to 0. That's a happy compromise to satisfy everyone. Negative 13 is clearly an integer. 3, a natural number. 10 over 11, that would be a rational number whose symbol is Q. That's the set of all rational numbers. 14, that's a natural number. Negative 13, an integer. Pi, well, let's ask ourselves, does pi ever finish or halt? The answer is no. There are in fact pi memorization contests all around the world. Some people take pride in memorizing many, many digits of this, or find peace in it. It never finishes. And it never repeats. It never gets stuck in a loop. This is an irrational number. Pi is irrational. But we would say that pi is a member, that's the symbol for membership, a member of the real numbers, because it's on the number line. Okay, 475 over 325. I better reduce this fraction because it looks like a bit of a trap. Okay, I'm going to divide them both by 5. And the trick to do that is to double them and then divide them by 10, because 2 over 10 is the same as 1 over 5. All right. So I'm going to double 475. The answer is 950, and 950 divided by 5 is divided by 10 rather is 95. And there you go. 325 doubled is 650. 650 divided by 10 is 65. And look at that, I can divide by 5 again. Okay. 95 doubled is 190. 190 divided by 10 is 19. 65 doubled is 130. 130 divided by 10 is 13. And so we find out that this is a rational number. A rational number. Rational numbers do not have a unique way of writing them, right? I could have put this or this on the page and they would have been seen as equivalent. 19 over 13 is called an irreducible rational number, and it's sort of seen as the representative of all these other rational numbers which are equivalent to 19 over 13. It's sort of like the most simplified version you can possibly get. Okay, square root of 77. Well, is 77 a perfect square? The answer is no. You should know your square numbers up to 10 squared, minimum. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. 77 is not a perfect square, so root 77 is irrational. And root 77 belongs to the real numbers. It'll be greater than 8, but less than 9. 6 over 7 is rational. The square root of 0 is 0 itself, which is problematic, or troublesome in this classification conundrum. So 0 is an integer. Nobody would dispute that. So I can write 0 belongs to the integers. Now, negative root 196. Is 196 a perfect square number? It is. I recommend, in fact, learning the square numbers all the way up to 31. Why? Because that's all the square numbers under 1000. 31 squared is 961. 32 squared is 1024. And by doing that, you gain an advantage if you have to factorize 3-digit numbers. But to stay on task, what's root 196? Well, the answer is 14. And so we get negative 14, and negative 14 is an integer. What about negative 1? Negative 1 is an integer. Negative 16 over negative 2. Well, you could say that when you evaluate this, when you evaluate it, you get the answer of 8. And so wouldn't it be correct to say that that this belongs to the natural numbers? It depends on your point of view. Some people view this as like an instruction. It's telling you to do something. Other people view this as an object that's just standing by itself. It's perfectly legitimate just to say negative 16 bar and then negative 2. So it depends on how you view it. It evaluates to a natural number, but the expression itself is a rational number because it's one integer divided by another non-zero integer. And now we have 135 over negative 3. And when we evaluate this, does 3 go into 135? Well, check out the numerator. 135 is on the 3 times table because 1 add 3 add 5 is on the 3 times table. That's a little trick to learn. 135 divided by 3 is 45. So this becomes negative 45. Negative 45 is a member of the integers. And this expression here, viewed as just a freestanding expression by itself, this here is a rational number. Okay, thank you.